Hello, class, and welcome to Survey of Calculus. We're going to say about sections of the textbook. These are a preview of calculus and function um, section. So let's take a look at. Let's go straight into some homework first. So I have your posted. This will be homework, and we want to get kind of an idea of what calculus is. Calculus deals with very small things and sometimes very small things being added together. So, actually, maybe I will just draw a couple of pictures first. So, for instance, the two biggest topics in a normal calculus class are going to be what is the slope of a function at a specific point? And the way we do that is we glue a straight line onto the function and measure the slope of that line. And the other thing we do is we try to figure out what is the area between a function and the x-axis. And we do that by making little rectangles that have the bottom side of them on the x-axis, the top part of them is touching the function, and then we take all of these little rectangles and we add them all together. So the first topic is called the derivative, and the second topic is called the integral. A normal calculus course will start by talking about an idea called the limit. The limit is what lets us find small things like the area of these small rectangles and the slopes of the correct line that touches the function in the correct way. And then after we talk about limits, we go into derivatives, usually for almost the rest of a semester. We touch integrals at the end of the semester, and then the next semester of calculus is basically using integrals. So a normal calculus class is going to talk about limits for a couple of weeks, talk about derivatives for a couple of months, and then talk about integrals for a couple of weeks. The next semester, you talk about integrals for a couple of months. Okay, so that's kind of what we're doing. First problem we have is number 24, and I do apologize. The version of the book that we're using has different problem numbers than when I got the problem set. So I am going to try and update all of those by next week. I do have the first homework assignment numbers up. I'm going to do problem 24, 2.1.24, which says want to sketch the function f of x equals the absolute x on the interval -1 to 2. So the absolute value graph looks like this, where this point is the point 1, 1. This point here is the point -1, 1. But we only want to graph the part that has x values between -1 and 2. So that'll be this point here at x is -1, comes down to the origin, and then it will go up to this point here, which is the point 2, 2, point -1, 1. These are straight line segments that connect at the origin. And we might as well label all of our x's like so. So that is Problem 24 says sketch that function on that region, and then it says shade the region between the function and the x-axis. So the last step will be to color this in. There we go. In fact, I might even make a hard border on the edges there, like that. So that's problem 24. Problem 25 says use the preceding exercise. So this is problem 24. We want to approximate the area between the x-axis and the graph of f over the interval -1 to 2 using rectangles. So, rolling. There we go. So let's draw it again. I'm going to make this a little bigger so we can see some rectangles. Here's the point -1, 1. Here's the origin, add 0. And here is the 2, 2. Here's our x-axis, y-axis. Guess I missed that just a little bit. I think it's... Oh, let's... I can hit that right there. Here's our y-axis. And now we're going to make some rectangles. It says, for the rectangles, use the square units and approximate both above and below the lines. So we'll make a rectangle that goes above the line like this. Go above. So we're going to basically divide the x-axis into, let's say, we'll use 4 regions here, so we'll use 8 regions here to keep the spacing equal. And then the highest point in each region will become, I don't know if I can draw this proportional. Okay, so we have 8 rectangles on the right side and 4 on the left because the right side is twice as wide. The right side is twice as wide as the left side. We could have split it into 2 on the left and 4 on the right. 1 on the left and 2 on the right. Maybe that's what it means by square units in the problem. That we're supposed to use whatever unit is being ticked off by the axis. I'm going to call an audible and say that that's what that. Here's 1 unit to the left at -1. Here is 2 units to the right at... We will make a rectangle that is 1 unit wide, and at the highest point in that region, we make top of our rectangle. The area of that rectangle is 1 times 1. In the next, where x is 1, this is where x is 2, this is -1. Here we find the highest point in the region, connect it across. We get a rectangle that is 1 unit high and 1 unit wide, so that is 1 unit. And then in this third region, highest point here is 2 units tall. It is 1 unit wide, so the area of this rectangle is 2. And that means that the upper estimate of the area is 1 plus 1 plus 2 is 4 units. On the other hand, if we do a lower limit, the lowest point in this region from -1 to 0 is 0. So we get a height of 0 and a width of 1. The lowest point between 0, x is 0 and x is there, so we get a height of 0. 0 times 1, 0. And the lowest point in this region goes from the point, this is a point, 1 unit of height. We have 1 unit of width, and the area of that rectangle is 1 times 1, which gives 1 unit of area. What we're doing is kind of like, well, it's actually pretty much a Riemann sum, which is how you approximate areas under curves. Of course, with straight lines, we already know that we can get an exact value. Might as well do that as we're working on this. We have a base of 1 and a height of 2 on this triangle, so we get 1 half times 1, or 1 times 1. This is a height of 2, a base of 2, so we get 1 half times the base height. We get 1 half plus 2, 5, is the actual area we get that via geometry. But the beautiful thing about calculus is you can basically sum it up as if you can make an approximation and then you can prove that there are ways to make your approximation better. Then you can prove that using your limit, you can get an exact answer. So let's draw a picture of what I mean. I have used 3 rectangles to find the area of this graph, the area between the graph and the x-axis. This is the area I want. I approximate it by making 3 rectangles and adding them together. I can show that I can get a better approximation by using 6 rectangles, let's say. Because my current approximation is going to overestimate by the value of these regions here. But if I split into smaller widths, then I will overestimate by less. So now my overestimation is only this region here, which is smaller than the original blue region by this much. I colored the wrong. There we go. So I can clip out that chunk and that chunk. That chunk, and get a better approximation by dividing the rectangles into smaller widths. And if I keep splitting the rectangles into smaller widths, I get better and better approximations. And then the limit process lets us get an exact value. And you might wonder, why do we want to do this for things that we can solve in geometry? The answer is you don't. You'd rather use geometry for the things that can be solved with geometry. These are nice straight lines. You should use geometry on that. Problem is, what happens when our functions aren't straight? And we need to find areas that are not nice geometric shapes like we studied in geometry. That's where you need calculus, because you can set up an approximation using these Riemann sums, these rectangles, and then you can prove that when you split the rectangles into smaller pieces, you get better approximations, and then you take a limit, and that limit gets you the exact area of the curve. So let's continue. We looked at problems 24 and 25, 4 through 27. Let's look at 26 and 27. So we're going to sketch a graph. The graph is square root of 1 minus x squared. So that's going to end up being a semicircle. Here's the point negative 1, 0. Here's the point 0, 1. Here's the point 1, 0. And it's this half circle. And again, since it's a circle, we could use geometry. We know the area of a circle is equal to pi r squared. But we're building up our calculus intuition. What you're going to have to do, so this is the complete answer to problem 26, just drawing the graph there. 27, the answer to that one is going to be, and you should use, I would recommend using like Desmos. Type this equation, y equals the square root of 1 minus x squared into Desmos to get the graph. And then what you're going to do is you're going to plug in x values starting at negative 1. You're going to split this into 5 chunks. So you're going to get a rectangle when you plug in negative 1. You get out a height of 0. When you plug in negative 0.6, you're going to get out probably a very bad looking decimal, but you'll get a height. Plug in x equals negative 0.6 into this equation. You're going to get a rectangle, whatever height comes out of the function. And then you're going to plug in another one at negative 0.2. That'll be here. You're going to plug in another one at positive 0.2 here. You're going to plug in x equals 6. And you're going to plug in x. I'll get you in. And then you're going to find the area of these rectangles. Their width is 4. Their heights are whatever you got when you plugged this into Desmos with x's values. The height of the rectangle times the width, which we saw as 4, is equal to the area of that rectangle. You add up the areas for the 3 rectangles. That gets you your lower estimate. For the upper estimate, you plug in higher value on each side, so the height of the original second rectangle, height of the first. And you'll get these rectangles to be just a little bit taller. You do it again. Now you have 5 rectangles, and you add those together. That'll get you your upper estimate. And again, like, since you're in a calculus class, you probably know how to multiply. You don't need to worry about multiplying by hand on this problem. The numbers will be a little bit crunchy. So feel free to use calculator and Desmos. That's the end of section 2.1. That should give you a preview of the kind of problem that is hard without calculus, that when you get to chapter 5 and we have both the limit and that to develop the integral, you'll see that these problems are a lot easier with this than with. Okay, so let's look at section 2. This is function. Question 6. The directions for these problems directions for 46 to 49, we're going to look at a graph, so I am going to grab a go, and then we're going to compute some limits. It says, following exercises, consider the graph of the function, which we have here. Which of the statements about f of x are true and which are false? Explain why explain why the statement is false. So the first statement is 46. We have the limit as x goes to 10 of f of x equals 0. And this is a lot of extra notation that you could read about in the chapter, but let's break this down a little bit. This color. So this set of symbols means we want to talk about a function, and we want to talk about the values where x is close to 10, but not exactly 10. Okay? So when we look at this graph here, we want to look at all of the points that are x values that are near 10, but aren't 10. These are the two chunks of the graph we want to look at. Okay? And we want to see if we are sliding along the graph from both sides, what is the y value that we come towards as we get closer and closer to 10? Well, that y value is pretty clearly 0. As we come down this side, this side of the graph, the y values go down until we get to 0. From here, we're going up until we get to 0. So this one turns out to be true. This is a true statement. But let's take a look at the other parts of the graph to get some intuition about how limits work. So let's start with looking at this point here. If I follow the curve this way, the y value I get close to is -6. If I follow the graph down this way, so this is from the right, from the left. You know which side is which. I do have trouble sometimes. From the right. If I come from the left or from the right, my y values shrink on both sides until I get to -6. We can think of it as like the function is pointing at -6, even though the function's value is somewhere else. So when we're talking about limits, we're talking about kind of the motion the function has, not the value the function actually attains at a point. So the limit, say the limit as x goes to -8 of f of x equals -6, even though f of -8 is this point here at -3. The function's value and the function's limit do not need to be equal. In this case, they aren't. But in 46's case, the limit of the function is 0, and the value of the function at 10 is also 0. So just select that. We'll paste a new. So the limit and the value do not have to be the same. In fact, sometimes the value doesn't exist at all, but the limit does. Sometimes the limit doesn't exist at all, but the value does. So let's move on to 47. We have the limit. The limit as x goes to -2 from the right. That's what that plus sign means. It's from the right, meaning we're not looking at. In 46, we cared about coming from both directions. In this one, we only care about coming from the right. F of x equals 3. So we're going to look at this -2. Here's -2. We're going to come from the right side. And the y value that we point at is definitely not a y value of 3. We're pointing somewhere up there. Usually when we draw a graph this way, we mean that there's an asymptote there. The function's going off to infinity. This one is false. And then we have to write a reason why it's false to do the problem. So f of x goes to infinity as x goes to -2 from the right. (48) have the limit as x goes to -8 of the function. Oh, is the limit as the limit of f of x as x goes to -8 equal to the function value at -8? We already said this. Function's value is here, but the limit is down here. This y value is -6. This y value is -3. Those are not equal. This one is false. In later sections, we will learn a term for when the limit equals the function. Well, we'll learn the term now. It's called continuity. When the limit equals the function, we say the function is continuous. We'll get more into that later on. But this this function is not continuous. I feel I can let you do. Oh, okay. Let's look at 49. 49, we have the limit as x goes to 6 of f of x equals 5. So we're looking, this is a limit with no decoration here. That would be from the right. This would be from the left. When there's no mark there, you look at both sides. So coming to x equals 6 from this side and from this side. The limit from the right equals 5. The y value of that point is in fact 5. From the left, our limit is 2. So the limit as x goes to 6 from the left of our function is 2. When the right and left limits are not equal, we say that the limit doesn't exist. This is a false statement. The limit as x goes to 6 of f of x is not 5. The limit does not exist. Or sometimes we just say dn. Notice the function doesn't equal dne. Dne is not a number, so you can't equal it. It's just this limit doesn't exist. Scroll through. Set of problems is 64. Those are more 1 and 2-sided limits. I'll let you do. If you have questions, send me a or send me a message and I'll help you out. But I think that you can probably handle them after reading the chapter and doing some of these problems with. The last problem in this homework set is 46. It says, in the following exercises, sketch the graph of a function with the following properties. Let's write those properties down. Have the limit as x goes to 2 of f of x equals 1. The limit as x goes to 4 from the left of f of x is 3, and the limit as x goes to 4 from the right is 6. And the last property is f of 4 is undefined. Okay, so a lot of stuff happening at 4, so let's mark 4 tick marks. From the left side, we want to approach 3, so let's count up 1, 2. Right, we'll need 6, so we'll want the lines pretty each other. 1, 2, 3. We want to approach there on the left side. On the right side, we want to approach 6. So we're going to have here, we want this limit to equal 1. So here's 2, here's 1. Let's just pick that like that. And since this is a two-sided limit, notice there's no direct decoration there. We have to come that same height of 1 on both sides. It says, so now we have this limit is true. The limit from the left at 4 is true. The limit from the right at 4 is true. We want to make sure that f of 4 is undefined, so we don't put any solid dot in that vertical x equals 4 row. Just do that. This would work. There are lots of things we could do. Notice it didn't say that f of x had to equal 1 at 2. So we could make this a hollow dot and put a solid dot somewhere else if we wanted. But it's fine. This works. I'd recommend practicing several of these types of problems. Make sure that you got it. Let's do a little bit of a preview in 2. Up now. Points from, or more problems from homework 2, probably on Friday, as I'll have time to record some more. Let's see. That homework starts in 2, 3, 5. Okay, work. So this is 2.3.93. We want to find the value of the limit as x goes to 4, x squared minus 16 over x minus 4. So we're going to learn a bunch of limit laws. I have videos of the limit laws already on this channel. So if you want to look at those and get a preview, then that's great. Otherwise, I'm going to go over more limit laws on Friday. But basically, the way that we're going to calculate limits in this class is we're going to try and do some sort of algebraic manipulation of the argument of the function that's inside the limit until we get it into a state that we can use continuity to evaluate. That's the normal procedure for it. So the first thing I'm going to do is I'm going to factor the function inside of this limit. It's x plus 4 times x minus 4 over x minus 4. Just factored the numerator. I can now cancel the common factor from the numerator and the denominator. The limit as x goes to 4 of x plus 4. And if I plug 4 into this x plus 4, I'm going to get 8. Lines are continuous. Continuous means the limit equals the value. So the value of this line is 4 plus 4 equals 8 when I plug in my x value of 4. The value of the line is 8. Lines are continuous, so the limit equals the value, and I get that. Not all functions are continuous. Most functions are not continuous. But here are some really nice functions that are continuous. Linear functions are continuous. Polynomial functions are continuous. Trigonometric functions are continuous where they are defined. Trigonometric. Exponential functions. Logarithmic function. And arc trigonometric function. Did I miss anything? Oh, root functions. Again, these are where they're defined. So like if you're looking at the square root function, here's y equals the square root of x. There, it's not defined on this half of the graph. So it's not continuous here. But like this is a very nice category of functions that are continuous. If you can rewrite your function to look like one of these, then you have a continuous function. You can easily compute the limit. That's really nice. So we canceled out this term here, and it allowed us to compute a limit. We couldn't do that directly because this rational function has a 0 in the denominator here and a 0 in the numerator here when you plug in x equals 4. Notice I get 16. 16 on top is 0. 4 minus 4 on the bottom is 0. 0 over 0 is what's called an indeterminate form, meaning you can't compute a limit if you get 0 over 0 or infinity over. Those are the two common ones that we're going to deal with. So if you plug in a function, if you have a limit as x goes to some number of some function, if you try plugging the value into the function and you get 0 over 0 or infinity over infinity, you have what's called an indeterminate form. And that means you're going to have to use some algebra to rewrite. Usually that takes the form of factoring and canceling. Once you've done that, you should be able to plug the number in and find the value. Let's do another one. I don't want to do all of your problems of this type. I'm going to do 97. 97 is a hard one. Still the same idea. Not one you're assigned, but it's harder than the ones that I assigned for home. Limit as t goes to 9 of t minus 9 over the square root of t minus 3. Notice, if I try and plug in 9 right now, I'm going to get 9 minus 9 on top, and the square root of 9 minus 3 on the bottom is 0 on the top, And square root of 9 is 3. 3 minus 3 is 0 on the bottom. Determinant. Indeterminate comes from determinate means like to determine, to tell, to tell if something is or is not a thing. So indeterminate means not able to tell. That's why it's the word. It's not able. We're not able to tell the limit. It's indeterminate what the limit is. So I'm going to have to rewrite this in some way, get it out of this form so I can solve. I'm going to do something called rationalizing the denominator, which is a technique that you should have been shown in your college algebra class. Just going to multiply by something that's a creative expression that equals creative way to write 1. I haven't done anything, but I'm going to multiply by the square root of t plus 3 over itself. Notice the top and bottom of this fraction are the same, so the numerator and denominator are equal. This equals 1. When I try and multiply that out, use my distribution, my foiling, square root of t times square root of t is t. First, outside is plus 3 square root t. Inside, minus 3 square root t. And then last, negative 3 times positive 3 is negative 9. On the top, we also multiply. We get e square root 3 plus 3t. I don't really have to multiply this part out. I can't just leave it fat. Bottom is the important part. I guess I'll multiply it out. E root 3 plus 3t minus 9 minus 27. I don't technically multiply that out. I'm just going to. Here, I notice that negative 3t and positive 3t cancel. Yeah, I probably shouldn't have multiplied that out. If I had not multiplied it out, it would have been left as e minus 9 times square root of t plus 3. The bottom becomes just t minus 9, and that cancels. At this point, I have the limit as t goes to 9 of square root of t plus 3. I plug the 9 in, get square root of 9 plus 3. Square root of 9 is 3. 3 plus 3 is 6, and that's my limit. It's not too that'll be I'll do the 2.4 homework in my other video on Friday. Hope that you're all doing well, and good luck on this homework. I hope you enjoy calculus. Bye.